Hello everybody, Sulcan here and welcome to Games with Python. And today we are going to talk about a Sudoku solver using backtracking algorithm. We will start off with an introduction which involves the thought process in creating our code in a Python script. And if you wish to skip to the coding part, which I suggest you shouldn't, you may do so by checking the timestamps in the description. Sudoku is a logic-based combinatorial number placement puzzle. The game is played on a 9x9 Sudoku board, which is subdivided into 9 3x3 boxes. The objective of the game is to complete a partially filled Sudoku board where each row must contain the numbers from 1 to 9 without repetitions, each column must contain the numbers from 1 to 9 without repetitions, and each box must contain the numbers from 1 to 9 without repetitions. There are a number of ways to solve a Sudoku puzzle with automation. One of them is with backtracking algorithm, where you can solve the puzzle in few or split of a second. The idea behind the backtracking algorithm is that it incrementally builds candidates to the solutions, and it abandons a candidate as soon as it determines that that candidate cannot possibly be completed to a valid solution. To better understand this algorithm, let's dive in with an example. What we have here is a partially filled board, almost complete, with just 3 empty cells remaining to be completed or filled. The algorithm will first find an empty cell. It will then fill that cell with values from 1 to 9, starting with 1. Next, it checks if the trial value of 1 satisfies the game rules. If it doesn't satisfy the rules, then it's not a valid solution, and we'll try the next trial value 2. Otherwise, if it is a solution, then it is a candidate to the solutions, and we'll attempt to solve the rest of the board. Unfortunately here, it doesn't satisfy all the rules, and so we try the next value 2. Upon checking, the trial value of 2 does not satisfy all the rules, and so we try the next value 3. Upon checking this time, the trial value of 3 satisfies all the rules except 1, the column constraint. Therefore, we try the next value 4. However, the trial value of 4 does not satisfy all the rules. Again, we try the next value 5. At long last, the trial value of 5 satisfies all the rules. Thus, we consider the value 5 on that specific cell as a candidate to the solutions of the puzzle. Please note though that satisfying all the rules of the game on an empty cell doesn't guarantee a solution to the puzzle. It just so happens that our example is almost completely filled, which limits the number of possible values on each empty cell. In a practical Sudoku board, an empty cell can be satisfied with many possible values at the early stage, but only one or few of them are valid at the end stage. Hence the use of the phrase candidate to the solution. Moving on, we now have this candidate to the solutions Sudoku board, and from the initial board with 3 empty cells, we are now down to 2 empty cells. We can just solve the rest of the puzzle just like how we did earlier, and if you can notice, this repeats the solving process, and this is where the recursive part of the algorithm comes in. First, we find an empty cell, then try the values from 1 to 9, starting with 1, and we see that the trial value 1 does not satisfy some of the rules, so we try the next value 2. The trial value 2 does not satisfy some of the rules, and so we try the next value 3. And now we see that the trial value 3 satisfies all of the rules, and so we consider this as a candidate to the solutions. We now have this new Sudoku board, which is a candidate to the solutions, and we try to solve the remaining empty cell. Again, we first locate the empty cell, then we try the values from 1 to 9, starting with 1, and we see that the value 1 does not satisfy some of the rules, so we try the next value 2. And the trial value 2 actually satisfies all of the rules, and so we consider this as a candidate to the solutions. Finally, we have this candidate to the solutions Sudoku board, and as you may notice, there are no longer any empty cells in our Sudoku board. This is the prime determinant that the puzzle is solved. Thus, from a candidate to the solutions, we now consider this as an actual solution to the puzzle. Puzzle solved. Well, I hate to bring it up to you, but we are not quite finished with our algorithm yet. In actuality, this is not always the case. It is most probable that we may hit a dead end, meaning that our candidates aren't really valid, or there are more solutions to the puzzle, not just one. And so we must continue with our algorithm. So now, after evaluating the Sudoku board, we go back to the recently or previously updated cell, and then we continue with the remaining possible values to find for an alternative solution. In our example, however, trying the remaining values from 3 to 9 actually doesn't satisfy the rules of the game, thus none of them is a solution. What we do now is we are going to free that cell back to an empty cell and rewind the Sudoku board back to its previous state. Now, we are back to a Sudoku board, which is a candidate to the solutions, with one empty cell. In a sense, we are doing a backtracking logic from where the algorithm derived its name. And then, we repeat the process. We locate the recently or previously updated cell and continue with the remaining possible values for an alternative solution. However, trying the remaining values from 49 doesn't satisfy the rules of the game yet again. And then we free that cell back to an empty cell and locate the recently or previously updated cell and try the remaining possible values, but in doing so, none of them really satisfies the rules of the game. And then we free that cell back to an empty cell. At this point, we are back to the original state of the Sudoku board, which signifies the end of the algorithm. To reiterate, there may be one or more solutions to a Sudoku puzzle. It is also possible for a Sudoku puzzle to have no solution at all, but that will be a bad example. Most Sudoku puzzle generator actually checks for solutions before it publishes a puzzle. Thus, most often than not, you'll encounter a Sudoku puzzle with at least one solution. Moving forward, let's develop the pseudocode based from our example so far. First, we find an empty cell, and then on that empty cell we try the numbers from 1 to 9, and for each number we check for its validity against the rules of the game. Then, if it is valid, we create or update the new board, which represents the candidate to the solutions of the puzzle. Then we're going to perform the backtracking algorithm to solve that new board, which is the recursive part of the algorithm. And lastly, we're going to revert the board back to its previous state to check for alternative solutions. And before we forget, we have a base case where if there are no more empty cells in the board, then the puzzle is solved. Now, before we start our code, let's understand the data structure that will hold our Sudoku board data. We'll be implementing our Sudoku board as a list within a list, as it is fairly the basic representation of a two-dimensional structure. We will be referencing the rows from the top to the bottom as 0 to 8 respectively, and the columns from left to right as 0 to 8 respectively. These will be used partly to check the two rules of the game. We then check for the 3x3 boxes for the last rule of the game. This is somewhat tricky as it involves a tiny bit of math, but overall, not very difficult to understand. We identify the boxes based on their arrangement or indices in the Sudoku board, with rows from top to bottom as 0 to 2 respectively, and columns from left to right as 0 to 2 respectively. Let's take a cell for example with index 5, 7. the cell row index being 5 and the cell column index being 7. We want to identify which box this cell belongs to. How do we get the box indices, you ask? Simple, with the use of a tiny bit of math. What we have here are the computations to derive the indices of the box to where the cell 5, 7 belongs to. As you can see on the first line, the box row index is simply just the cell row index integer division by 3. Usually when we do division, we get a whole number value and a remainder, like 5 divided by 3 is one whole number with remainder 2. The integer division simply takes the whole number and completely ignores the remainder. Thus, the result from the operation is 1 for the box row index. You may also ask why we use integer division by 3, and the reason for that is because we are dealing with a 3 by 3 boxes. We then use the same computation for the box column index, but this time we use the cell column index integer division by 3. That is 7 integer division by 3, which is simply 2 whole numbers with remainder 1, and by ignoring the remainder, we get the value of 2. Thus, the cell 5, 7 belongs to box 1, 2. You can check the computation for the other 80 cells if you want to verify the formula. Now, we also have to do a reverse of our previous formula to find all 9 cells within a box. To do this, let's first try to understand the relation between the cell and the box, with box 1, 2 as an example. Cell 5, 7 actually has row 5 and column 7 when referenced to the 9 by 9 Sudoku board. But if you think about it, it is just cell 2, 1 when referenced to the 3 by 3 box that it belongs to. From here on, we define R and C as the row and column indices of a cell, respectively, as reference to the box the cell belongs to. So for cell 2, 1 inside box 1, 2, the box row index is 1 multiplied by 3 and then added with R of 2, which is the cell 2, 1 row index. From there, we get the cell row index of 5, which is the index in reference to the whole 9 by 9 Sudoku board. Then, we do the same for the column with box column index of 2 multiplied by 3 and then add the C of 1, which is the cell 2, 1 column index, and from there we get the cell column index of 7, which is the index in reference to the 9 by 9 Sudoku board. And with that, we are finished with the introduction. Now, onto the code.